Hello everyone, welcome to Statistical Foundation for Big Data Analysis. We continue with our module on statistical learning theory. We continue our discussion on bias, variance, mean squared error. In last class we defined bias, variance and total error, but today, and also we discussed some examples. The examples we discussed were rather pathological types, just to exemplify the calculations that we have to do, the type of expected value we have to calculate, just to underscore expectation given what, expectation of what given what has to be calculated to calculate each of these components. Today we move on with some real life example, slightly more practical oriented example, but like just as before, this is our model. You have x and y. Before we start, just to reiterate, I will just recall this law of iterated expectation for random vectors. If you have x and y and you have a function of xy, gxy, the expected value of gxy with respect to the distribution of y given x is actually a function of x, because you are fixing x, then you are taking expected value with respect to the conditional distribution of y given x. So, you are averaging out for all y, all y's that are allowed if you fix that x. So, y's are getting added up. So, you get a particular value for every fixed value of x. Now, this becomes an function of x, the one inside the bracket. This function of x, now if you average this one out with respect to all possible values of x, this gives you this iterated expectation, namely expectation of expectation with respect to the distribution of x of expectation of gxy with respect to the conditional distribution of y given x. This iterated expected value is nothing but the unconditional expected value of gxy when you take the whole distribution. Now, the inner expectation averages gxy over the conditional distribution of y given x, and the outer expression averages the marginal distribution of x. So, this is how the expectation of gxy can be calculated with respect to the unconditional distribution of xy. Now, let us be back to our learning theory setup. You have a data x1, x2, x1, y1, x2, y2, xn, yn. This is being collected from joint probability distribution xy. You want to come up with a rule y as based, you want to come up with a rule for y equal to hsx to model y in terms of x given the sample data s. Now, note that y takes values in R. We introduce an algorithm A on this data to learn a hypothesis hs, that is a guess, an educated guess for the relation between y and x. This is has been our model. Now, let us restrict to the IID sample case. I mean, last time we kind of discussed fixed situation where your sample were allowed, like you were only getting 3 particular sample. Now, let us assume no such pathological condition, just S be any sample, any IID sample of a fixed size n from the same population as the distribution of x, y. So, this makes S a function of x, hs a function of s, and hence a random variable. We define the conditional expectation of y given x as this expectation of y with respect to its conditional distribution given s. For a fixed sample, you define the total expected error with respect to the distribution is like you take the hypothesis or the rule that you generate by the algorithm given that sample as an input, the hs. Now, for every x value, predict y using this rule. So, take basically this prediction for y, hsx for every x, and then take the square difference between hsx and actual value of y. So, that is gives you hsx minus y whole square. Take the average of this over the whole sample. That gives you the, for a particular fixed sample, the expected test error. And expected value of your predictor h is nothing but just simply take the average of all the predictions. We discussed all these last time. So, our bias is basically take the average predicted value minus the average value of y, average predicted value minus average actual value. So, this is basically squared. So, this one squared difference between average predicted value and average value for all average actual. Y for all x. So, this is for all x, you are getting average predicted value of y and average actual value of y, fixing x and taking the squared difference of that, and now you are taking the average of that. So, if you think of population as this whole population of x y as something this big, and let's say this is for a particular value x, this is your population center, this is x y. Suppose for this is your x equal to x, this is your population center. Now, the rules you are getting for various samples are so. So, this is your whole population for x equal to x. Let us say these are the y values, this is your expected value of y given x equal to x, this is your population center. Now, the rules you are getting, let us say these are these are your predicted values. Now, here this is your average of the predicted values. So, these are H S1, H S2, H Sn and so on, H Sk and so on. So, these are your predicted values for y. You are taking, this is your center, this will be your average predicted value. Now, you take the squared difference between these two. Now, vary this for all line, take the average over all line. This is going to be your this value bias. So, you take the average value of y fixing x, average value of all the predicted values for y fixing x, take the squared difference of that, and now do that for every x and take the average. This is your bias. The variance we defined. So, this was our bias, the difference between, when we discussed bias, I think sometime at the beginning of lecture 17 or something, like the second lecture of this module, I think, we said the bias is the inherent difference between what algorithm is trying to predict. Algorithm, as I said, like algorithm searches, algorithm after all is a finite thing. Based on the sample, whatever the input you do, it tries to search, it can only search amongst the finite, in a finite domain. In that finite domain, it is searching models, let us say amongst the finite possible models, and it is looking for the best model that fits that sample. Now, for every sample, it is only searching in that finite domain only. So, in that finite domain, when you are taking feeding over the samples, you find a center of that search space, whereas there is actual center in the population. The difference between this search space center and the population center is your bias. Variance is essentially the spread of the search space. How spread potentially that search space? Well, not really the, well, not really the spread of the search space, but the spread of the points in the search space. In the search space, you look for the points which are touched by some sample. For population, the algorithm finds searches in a finite search space. For every sample, it touches one of the points in the search space. Just take the points which are potentially touched by the sample. Bias is center of those 2 points, that data cloud, and the actual center of the population. And variance is that, like, whichever points in the search space is touched by the algorithm for various samples, take that collection of data points and the spread of that. That spread is your variance. That is a spread, that is difference from, if that is very big, that means the algorithm is not giving you very precise prediction. For various samples, the prediction is becoming different. And if the search space is, the center of the search space is very far from the center of the actual population, then the prediction is not very accurate. So these are the 2 potential errors that are involved in the in your prediction process. In fact, one big theorem that we are going to prove in these 2 models, in these 2 modules, I think the beginning, and I think I will prove this in the first module of first class of the next module, namely the statistical learning theory 2, is going to be the bias variance decomposition theorem. We will see that, like, basically the 2 key components of error in model prediction, the prediction using a particular algorithm, are this bias and variance. So these are 2 very key components of prediction. Now this is your expected total error, where you are taking the predicted value minus actual value, the square difference between them, and you are taking the sum over all possible data points as well as all possible sample. So this is your total test error. So now let us discuss one practical example. Suppose X is the area of house in some in some unit, and Y is the price of a house. And suppose it's reasonably well that a linear relation between price of a house as well as area of the house. So price of a house can be reasonably predicted in terms of area of the house in terms of a linear function. So suppose you assume that price of a house in some unit can be predicted in terms of a linear function of area of a house in some unit. Can be predicted nicely, meaning the prediction error is basically centered around 0 and has some moderate variance. So when you predict Y in terms of X as a linear function, you know that Y equal to 100x plus 100 plus some error which is centered around 0. That is, the error can go up and or down, the difference between this predicted model as well as the actual value can potentially, it is not always positively biased or negatively biased, but it's the error has center at 0. Now also you assume X can potentially take 3 values with same probability. It's discrete uniform with values 0, 1, 2. So generally, you know, the houses are generally come with, like, builders make houses of this many square feet, this many square feet, this many square feet, and so on. So X takes values 0, 1, 2, let us say fixed, there are 3 potential values for X, each has same probability 0, 1, 2. So this already gives you the distribution of Y. The epsilon follows distribution normal 0 sigma square, that is, for a particular fixed value of X, Y becomes normal with mean 200x plus 100 and variance sigma square. So you observe a random sample, let us say you are observing a random sample of size 3, where x1, y1, x2, y2, x3, y3 are your sample points. So each xi is drawn uniformly from 0, 1, 2, and yi is 200 xi plus 100 plus some error term epsilon. You know the distribution of yi in terms of, because you know the distribution of x epsilon I, so you know the distribution of yi. Now, suppose we fit a linear model. So, based on these three values, suppose you are fitting a linear model, that is a best line which fits this 3 points, best. That is, you do it in terms of this squared difference between the predicted and actual. So, you look for line for which the squared difference between actual value of yi as well as the predicted value of yi axi plus b, the square difference that is minimum. This is basically the least square fit. We discussed this earlier. So, the expected model for this is this h bar x, which is expected value with respect to all samples of hsx, the model that your algorithm produces based on this sample. Yes, in this case, of course, assuming that the underlying relation, actual relation between x and y can be fairly accurately modeled in terms of a linear relation, 2x plus 100, of course modulo some error term epsilon, which importantly has mean 0 and some finite variance. The expected value of this prediction, mean prediction actually is same as 2x plus 100. That is what we saw. But I just mentioned earlier that it follows from properties of least square fit. The bias then will be expected value with respect to x of h bar x minus expected value y given x, and expected value of y given x, remember y is, we assume that it is 200x plus epsilon, where 200x plus 100 plus epsilon, where epsilon follows normal 0 sigma square. We saw that from here it follows like expected value of y is nothing but just this 200x plus 100. So, expected value of y given x, of course, given x, it follows from here that 200x plus 100, because x is constant, so this part is constant, comes out, and expected value of, and epsilon is this for all x plus epsilon which is 200x plus 100, because expected value of epsilon is 0. So, we saw this. Now, variance of this estimator is this. Variance will be, you take the variance of hsx with respect to the distribution of x. So, this is, we are writing it for simplicity to avoid cumbersome notation, but whenever we are writing expected value of variance, variance of something, what we really mean that expected value of x, here you are taking variance with respect to s, meaning you are fixing x equal to something. You are taking variance of this in whatever is there with respect to s only, fixing x equal to some value. That means take the conditional distribution of s fixing x, and then you are taking expected value with respect to x. But why is that so? I mean, previously in some previous slides we saw a slightly different expression for variance. Namely, we saw that the way we write variance, we wrote variance as expected value with respect to all possible sample and all possible x's of predicted value minus average predicted value of a particular sample minus average predicted value. You take the square difference between that and take the square. Now, from where, how do you get this? This is a big question. So, let us see how we get this. So, let me explain in a cleaner paper. So, variance by definition was expected value with respect to variance of model of algorithm. Our algorithm was defined as of your specific prediction minus average prediction and the squared difference, you are taking expectation of that. Now, we observe that expected value of for any two z1 z2 z1 z2 of any function g z1 z2, this was the law of iterated expectation. This is nothing but expected value of z1, expected value of z2 given z1 equal to something, I mean just take any conditional z1 of g z1 z2. So, you take the this expected value of g z1 z2 with respect to the conditional distribution of z1 z2 given z1, that is fix z1, and take the distribution of z2 when z1 is fixed to something, that is the conditional distribution. Take the expectation of g z1 z2 with respect to that distribution. Because z1 is fixed, this becomes a function of z2 then. So, you just take the expectation with respect to that conditional distribution of z2, then you get a value. Now, for every fixed z1 you get a value. So, this becomes some function, well not use h because h is being used for our algorithm. This becomes some function k z1. For every z1 you get this value, this k z1, and then you take the expected value of k z1 with respect to, of course, the marginal distribution of z1. This actually gives us unconditional distribution. This is what we saw. Now, if you want to apply the same process on the variance, what you can do, you can keep the x inside and take the expected value of s given s equal to x, hs x minus h bar x whole square. But what is h bar x? H bar x is nothing but expected value with respect to x when you keep x fixed of hs. So, if you view this here, this is nothing but variance of, so this is nothing but, so this expression now, the one inside the bracket is nothing but variance of, or let me just write carefully, variance with respect to which distribution. This is nothing but variance with respect to the conditional distribution of s given x equal to x of hs x. Why? After all, variance is just expected value of the random variable minus its expected value, but this is the expected value of this random variable with respect to this distribution. So, this is how you get the variance. So, this is how your variance of the model simply becomes this variance. Now, the variance of course will increase if the housing market is noisy, if there are some inherent variability. If your training sample is too few, like if you are modeling with respect to very few data points, it will not have the smoothing property which having larger sample has, and the training areas are like unrepresentative. If your data is, the sample itself is unrepresentative, in these cases you may have bigger variance. So, and bias, we realize that, like we discussed what bias is. Bias is that expected value of average predictor minus the squared difference, the expected value of the squared difference between average predicted value and average actual value. So, discuss this bias. So, in case of linear regression model, that is when you are having bunch of data points, you just fit the data, fit the line which fits the least square, for which minimizes the squared distance between the predicted value and the actual value. So, we know that this is, we have this from something called Gauss Markov theorem. We will discuss this later. I just said this earlier also. This tells you that expected average value of this predictor actually gives you the underlying linear relation. That gives the underlying linear relation gives you actually the expected value of the when expectation is taken over all sample. That is Gauss-Markov predictor is unbiased. This is a theorem we will prove later in module 6 more rigorously. Now, this actually makes the bias very low for this module, namely the bias actually becomes 0 in this case. So, one can check that the h bar x is 2x plus 100 and also expected value of y given x is 2x plus 100. So, the bias, the difference between these two itself is 0. So, squared difference is always 0. It's a expected value of a constant random variable 0. So, it gives you 0. So, the real life meaning is the model is essentially unbiased. The average predictor, average of the prediction functions more or less matches with the average of the actual population. Of course, one of the reasons, I mean here one crucial thing to observe that our underlying relation is linear relation. That is an assumption we are making about the population, and we are trying to fit a linear model. That is a very artificial situation. If the underlying relation was, for example, polynomial or exponential and you are trying to fit a linear line, of course bias will appear. In fact, these things we will see in next few talks. So, now we have this as our variance. So, it measures how the prediction changes across various training samples. So, let us do some calculation. So, if this is your data set, like you have random sample consisting of 3 points just like we discussed before, and you are trying to predict this least square curve, you fit it using these 3 points, that is you find AS and BS using this by least square estimator. You want to find the variance of this thing. Now, variance of this thing will be when you take the expected value of the variance of this thing will be just this whole expression when you basically you are taking expected value with respect to x and s, you are taking hsx minus h bar x, you do this conditional expectation. So, this becomes conditional variance of s given x equal to x of this. Now, for a fixed house size, this measures how much predicted value fluctuates across different training set. Averaging this quantity over all x gives you this actual variance. So, high variance scenario will be very few training houses, large market noise, model is too flexible, that is noise, it fits the noise instead of the 2 pattern. If you have many training houses like large sample, that will potentially lead to low variance scenario. If the market noise, that is the inherent, this market noise here in both cases, but we are talking about market noise, this is essentially this, you wrote y equal to 2x plus 100 plus epsilon, this inherent noise, inherent disturbance that is coming from this epsilon is less. Suppose this is big, this is high variance scenario, this is close to 0, this makes you low variance scenario, and model is stable across the data set. Of course, I mean that is just the definition of variance, that if the model does not change too much as you take various data sets, that actually is the definition of variance. So, if it is stable with respect to data set, of course, the variance is less, and it is flexible, the variance is high. So, this is these are our results that we discussed. Now, the point is that like when you are trying to calculate this variance for the linear model, you know that your model is this Ax plus Bs. So, you are trying to calculate variance of ASX plus Bs, sorry for that there should be a Bs here. Now, you are trying to calculate the variance for this is just a sum. So, now sum of variance, you know that variance of Z1 plus Z2, it gives you variance of Z1 plus variance of Z2 plus the covariances Z1, Z2, and hence you get this expression. So, when you expand it out, you get this expression. Now, note that S involves, so S is a sample of size 3, x1, y1, x2, y2, x3, y3. When you are taking these numbers, these things you are trying to calculate, variance S, so variance of AS condition, variance of AS with respect to conditional distribution of S given x equal to x, variance of BS with respect to conditional distribution of x, and covariance of AS BS with respect to conditional distribution of S. For linear models, all these terms have closed form formula. Of course, AS BS simply has formulas in terms of the AS BS has closed form formulas in terms of the data itself, as we saw in some previous class. They have just explicitly, you find the sample mean and the values, and you take the squared distances between sample mean and actual values, etc., and you can calculate this. So, AS and BS are explicit functions, rational functions of the sample point. Now, you take expected value with respect to y. Y has a rather nice distribution once x is given. That tells you, once you take the y's, when you expect the y's out and take the variance with respect to y's, keeping x as fixed, these becomes functions of x's. Now, x's can take exactly 3 values. Now, sample is coming out to be a triplet of numbers. When you are taking y's out, when you are taking a sample by keeping x fixed, sample means you have x's and y's, all of them. What happens is that these things, these variances comes out to be functions of x's only. So, for linear models, they are functions of x1, x2, x3 only. I am not writing down the cumbersome explicit formula, but just remember that these 3 terms turns out to be the functions of the x values of the data only. Now, the fact that they are functions of x values of the data only, because x values x, after all xi, x1, x2, xn are they follow same distribution of x. So, this whole game becomes finding certain moments with respect to the distribution of x, but x takes uniformly 3 values 0, 1, 2 with probability 1/3. Expectation, variance, everything can be calculated using finite amount of calculation. In fact, this triplet x1, x2, x3 can take 27 possible values, each with probability 1/27. IID each takes 3 values, so 3 together takes 27 possible values, all with same probability. So, in this restricted model where y has nice linear, y behaves in a nice linear fashion with respect to x, you can potentially calculate. However, it shows that you have to add and subtract and multiply these 27 possible values, which potentially can be done using a calculator or a small software, but it gets somewhat cumbersome. So, this tells you that in a very specific linear model kind of setup where x only takes discrete uniform distribution with 3 value, there also variance computation gets very complicated. In this restricted, somewhat pathological but somewhat real life, the last class's examples were completely pathological, like just toy example. This one is bit pathological, bit real life, but one shows that more you get near the real life situation, even under strong theoretical assumptions like linearity, the calculations may become very clumsy. And this is linear model, so you have nice formulas for these variances of AS, variances of BS, and covariance of AS BS. It has nice formulas, and it turns out they only depend on the x components of the data. Even then, it gets pretty messy. So, in general, it can get very complicated. So, we will see some more examples in next class. Thank you. I will stop here.